Hello everyone and welcome back to a brand new episode of the Funtastic Academy with me, Ayush Prasad. Today, let's pick up from where we left off last episode by continuing to learn about Quicksort. Today, we'll analyze exactly how fast Quicksort is and in the process, learn more about why people call it the Quicksort. But before we continue, let's answer the quiz question from last episode. What problem was Tony Hall working on that led him to invent Quicksort in 1959? The answer is, drumroll please, translating a dictionary. Hall was busy translating sentences from Russian to English, but his translation words were all stored in order on the tape. So he had to sort every word to figure out in what order to read them off the tape. With that out of the way, let's see how fast is the ingenious algorithm that Hall devised. To answer that, I pass the mic to Computer Ayush. Thanks for that, Cam Ayush. Now I'm here to explain how to calculate Quicksort's time complexity. Before that though, let's do a quick recap of what exactly Quicksort does. In this top level algorithm, you can see it repeatedly calls the partition function and then quicksorts the lower and upper halves of the array. Partition divides the array into these two halves with a pivot separating them. Everything less than the pivot will go on one side and everything greater than the pivot will go on the other side. And then we simply sort both halves. The partition algorithm itself does most of the heavy lifting, separating the list and finding the pivot. Over here, we use the Lomuto algorithm. It effectively works by, in each iteration, consuming a next array element and swapping it either before or after the partition. Eventually, the pivot ends up in the right place. Now, we can start carefully analyzing how quicksort works. First, we need to find the time complexity of the partition function itself. And this is relatively easy. It just has one for loop going from low to high, -1, and then the last high iteration is handled by these lines of code at the end. So you could say that this inner portion is iterated for every element in the array between low and high. Of course, this if statement could skip a lot of that, but remember, big O time complexity is in the worst case scenario. So worst case scenario, all of this once, everything between low and high. And thus, we have to run this O of n times. Because there are no other loops and everything inside this is just constant time, we can say that a single iteration of partition is O of n, where n is the input. Now, we can use a similar structure to what we use when analyzing merge sort, which has a very similar structure. We can draw a diagram by taking the recursive function calls like a tree. We start with the full big list. Then we partition it into two sublists. We partition those again and again and again. At each layer of the tree, what is the time complexity we use? Well, in each layer, we have to partition everything at this layer. But this layer is just the sum of whatever was on this layer. And if you combine the two things on that layer, you get the top layer. So in each layer of the tree, each layer of function calling, we take O of the total size of the list. Even though each specific partition call could only deal with a few number of elements, there are going to be a lot of partition calls running in the same iteration. So thus, a single iteration of a series of partition will also be O of n. So partition iterations are also O of n. Now, comes the big point. How many iterations of partition are there? In merge sort, this was very easy because we are merging the list exactly into two in each iteration. Here it is harder. We don't know how many elements are going to land on each side when we do the partition. It depends on which pivot element we choose. Here I chose a good pivot element to make the analogy better. But we easily could have chosen, let's say, 7 as the pivot element. Then we would have 7 here, one element to the side, and everything on the other side, which would be bad because we have to sort this all over again. So, in the worst case scenario, we start with the initial list and then we partition it so that one side has 0 or 1 elements and the other has the full list again. And this just repeats. We always choose the greatest element in the list as our partition pivot, and thus we end up partitioning n separate times, one for each pivot we choose, until everything is partitioned. This ends up as a really inefficient form of bubble sort. We need to partition n times, and in each iteration, O of n cost to do the partition. Therefore, our worst case scenario would be O of n squared. So you might think, why are we even talking about this algorithm? Surely we just covered merge sort, which in worst case does n log n. Well, quicksort can actually be much faster than this worst case scenario. And now I'll show you how to calculate not only the worst case but the best and average case times for quicksort. And we'll see why quicksort is so efficient. So first off, the best case scenario. This is actually illustrated very well by the tree diagram I drew on the left. In each iteration, we cut the list exactly in half until at the bottom we are left with all elements of one list. And thus everything is sorted. So since each layer is O of n, we just need to count the layers. The layers is just the amount of divisions by 2 it takes to reduce the entire list down to one element. But we already did this with merge sort. It's just log n. In the best case scenario, there are log n layers, where we take the log 1 of base 2. Thus, in the best case scenario, we take n log n time to sort these log n layers, partitioning them on order of n. Now again, you might not see the usefulness of the algorithm. Its best case is the same as merge sort's worst case. But now I'll show you something interesting that we've not really done before. What's the average case? Now, what I'm going to do is say something completely ridiculous. I'm going to say that for a large enough list, the average partition ends up with 90% of the list on one side and just 10% on the other side. This side ends up with 9 out of 10 and the other side ends up with 1 over 10. Obviously, this has a very low chance of happening if we actually did the partition. You could say, on average, these would be closer in size. But I'm doing this to illustrate a point. See, now on each layer we reduce the size of the list by 90%. And sure, we do have these small 10% components, but these will get sorted quite quickly. They will be sorted quicker than the 9 out of 10 components because they're very small. So we just need to worry about the 9 out of 10 components. So as these 9 out of 10 go down and down, we need to count how many layers of 9 out of 10 they are, which is just asking, how many times can we reduce n by 90% until it becomes 1? But this is just like the question we were initially asking for log n. Only now, instead of reducing by 50%, we reduce by 9 out of 10. Now, we could look this at the other way, going up. We ask, how many times do we have to take 1 and multiply it by 10 over 9 so that we get our initial number n? And that number is just log of n with the base of 10 divided by 9. So now we know the number of layers, log 10 divided by 9. And surely, as you can see in this diagram, we need way more layers than in the log n example. In fact, the amount of extra layers we'll need will be the ratio between the amount we need here, log 10 by 9 of n, and log n, where we take the base as 2. But now here's the crazy part. Using the properties of logarithms, which is kind of difficult and maybe I won't have time to go to here, but we can actually show that this number ends up being a constant. We can show that all logarithms are proportional to each other. We can actually show that this ratio evaluates to be 1 divided by the logarithm of the constant number 10 divided by 9, where we take this logarithm as base 2. Now, this is a constant number. It doesn't depend on n. And you know what we said about constants in big O notation? They can be ignored. It doesn't matter if your algorithm takes n computer cycles or 1 billion n computer cycles. It'll still be a linear time. Because if we had a CPU chip that could speed up by this constant amount, it would be the same anyways. So really, in this really bad 9 out of 10 scenario, we can see that only ends up being a constant difference from the best case scenario. Now in theory, sometimes you could end up with something way, way worse than 9 out of 10. Sometimes one of these iterations could end up on a worst case scenario spread for some time. But it's possible to show that the likelihood of this decreases. I note that none of this argument is really specific to 9 out of 10. We could make this 999 out of 1000 or some number arbitrarily large and it still works. To actually find a real result, you need to look into something called amortized analysis, which is a bit complicated and it mostly comes to averaging what you expect each partition to go. But we can show that in the average case, Quicksort is again the same as its best case, an O of n log n algorithm. Why should you care then? Well, even if this might seem to have the same average time as merge sort's worst time, due to various implementation differences, it turns out that on most machines, Quicksort is way faster than merge sort when you actually count the cycles. This is because merge sort requires this extra memory, B, and also requires these extra loops and it's more complicated to do the merging. Meanwhile, Quicksort doesn't require any extra memory. It requires a little bit of memory in the stack to store each of these function calls, but in terms of the actual pseudocode, it doesn't need any memory. So because of that, Quicksort is called quick. It's generally preferred over merge sort, even though merge sort might have a better worst case time. And it's a good lesson that time complexities don't necessarily have to determine which algorithm is better. It also shows that you can use amortized analysis to derive some pretty interesting results. So to summarize, we figured out how to find the worst, average, and best case complexities of Quicksort. Finding that in the worst case, it's n squared, like the other algorithms we analyzed, but in the average case, it's n log n, blazingly fast. Now, I'll pass the mic back to Cam Ayush to outro you and give you the quiz question. Thanks for that, Ayush. Let's now recap what we learned. Over the past two episodes, we got introduced to the high level structure of the Quicksort algorithm and then learned how the Lomuto algorithm on a finer level successfully accomplishes partitioning. We then learned some parts of amortized analysis and used it to analyze how fast Quicksort is in big O notation. We found that it has an average time of O of n log n, and in most cases is much faster than merge sort for the same data, hence why it gets the name. Before I leave you, let me leave you with this one quiz question about Quicksort. We learned the Lomuto partition scheme over the past two episodes for its simplicity, but what's the more common partition scheme that engineers use for being much faster? Tell me the answer, and I'll see you next time on the Funtastic Academy. Bye!